Every Winter Olympics, the figure skating competition is a big draw, all the more so this year because of that judging controversy. But it is a combination of grace and acrobatics that most bedazzles us. And one move in particular, the quad. How does that happen? Here's NBC's Roger O'Neill.
It's the jump you have to do to win Olympic gold. The quad. 4 revolutions in 0.8 of a second. So fast, most spectators miss it. It's figure skating's most difficult jump, and you can always tell when a skater hits it just right. Like Tim Gable did Tuesday night. Crowned Quad King, the American is the only one in the world to land 3 quads in a single performance. Tell me the truth, though. Do you ever get dizzy?
It's not so much that you get dizzy, but when you come out of a spin, sometimes you get disoriented. Because if both sides look the same, you can't tell which way you're supposed to go always.
Gable has a perfect jumper's body. Medium height, thin, almost no body fat. But most important, narrow hips and shoulders, making it easier to spin.
You're not placing your top back, you're letting it cross.
Any jump, but especially the quad, breaks down into 3 key elements. First, rotational momentum. To rotate 4 times, Gable's ice speed has to be perfect, generate enough jumping energy. Too fast, too slow, the quad can't be completed. Jump height is the second element. That's not high for Gable, only 21 inches off the ice. Third and most critical, moment of inertia. The spin has to begin immediately, and to do that, arms and legs have to be tucked close to the body. The physics of how Gable's body moves through the quad amazes biomechanics expert Jim Richards.
He swings everything around. There it all uncoils, but as soon as he leaves the ice, the best part of it is how tight his arms are in.
And to achieve that spin rate is to bring everything together.
Everything's as tight as possible. What that does is it maximizes the rate of spin.
Richards says women don't do quad jet because they don't jump high enough, and they focus more on artistry. Gable's jumps have wowed the world, including his idol, gold medalist Scott Hamilton.
I'm proud of your son. He does a quadruple easier than I've ever seen anyone else do it. And it's absolutely in his blood. His body understands it.
Tonight, with the only realistic chance to win a medal for Team USA, Gable plans to do 3 quads, an Olympic first. Roger O'Neill, NBC News, Salt Lake City.
Okay, so here's a question for you.
Every tight his arms are in.
And to achieve that,
It's as tight as possible.
women don't do quad jet because they don't jump.
What it does is it
Richards says women don't do quad jet because they don't jump high enough.
Okay, guys, 21 inches. You don't think women can jump 21 inches with enough training? Yes or no?
They can.
Yeah,
They can't. Yeah, you don't need to be a sexist pig. Obviously, they should be able to, right? Gymnasts can actually do a lot better than that. So the question is, why is it that women cannot do quads, or can they? All right, so take a look at the date. This date is special because something interesting happened on that day. All right, March 11, 2011. I remember that day as it was yesterday because it was like 2 or 3 in the morning. I'm working on research. I was at Formula Lab at the time. In the background, as usual, you got news. That's CNN. So I'm watching CNN in the background, and then all of a sudden they cut to this. So there was a huge earthquake near Japan, and then it caused a tsunami. So they had the chopper just follow the tsunami.
Is this the one that broke the?
Go ahead.
Is this the one that broke the nuclear reactor?
Yeah, give yourself 5 points. Absolutely, this is the one. Messed it up. Anyway, so they cut to a different chopper. This is probably about 15, 20 minutes later. These townspeople were notified that the tsunami was coming, so they were asked to leave, evacuate the town, which they did. Most of them did, I think. I'm not sure if all of them did. So this is live on TV. This was on CNN. All right, so the town is being swept away as we were watching it. Okay, so one of the things that we will discuss next week's lecture is going to be mostly conceptual. You're going to find it next to impossible to swim these floodwaters when there's a tsunami. Even if you're an Olympic swimmer, you're not going to be able to swim in something like that. And if you're thinking the reason is because of debris, obviously debris has something to do with it. In reality, what happens is there's going to be a very strong undercurrent. Undercurrent is going to suck you under. So you're not going to be able to escape from it. So the question is, what caused the strong undercurrent? So that's something that we will discuss next week. It's just for this week, okay, look what's happening. You got the highways over here. Most people are still escaping. There's a couple of cars moving in this direction. They're trying to stay in front of this tsunami, flooding out to the tsunami, in essence. There's a guy standing up here. I don't know why they're standing up there, thinking that they are going to be safe. All right, so aside from the nuclear disaster that caused, what happened was because of this earthquake, days end up getting shortened, which means that the Earth ended up speeding up. All right, so what happened? The radius of the Earth actually shrunk by 6.7 inches. All right, as a result, the Earth ended up spinning faster, and consequently, we end up losing 1.8 microseconds per day. Okay, so remember, guys, the spin speed, the rotational speed of the Earth increased, which means that the Earth accelerated. So what caused acceleration? What caused acceleration is the force itself. The external force itself is what causes it. So if it's the rotational acceleration is going to be caused by a rotational force, torque. In this case, there's no rotational force or torque acting on the Earth. So in the absence of a rotational force, in the absence of a rotational external force acting on the Earth, what caused the Earth to actually accelerate during the earthquake? Okay, so this is projectile motion. It's predictable motion, right? It's predictable 100%. Given the fact that this is 100% predictable, why is it that this guy is falling short? This is not supposed to be working out this way. He's supposed to be landing on top of these cars. There's an X here. This guy is falling short like by 20 yards. How's that even possible?
Human error.
Go ahead.
Didn't reach the
Like, didn't
top
reach.
speed.
All right, so you guys kind of broke up. All right. Okay, number one, why should this motion be predictable? It's predictable because gravity is the only force acting, right? Only one direction. On the X direction, ignoring air friction, acceleration should be 0. And for the most part, you can make that assumption that the acceleration on the X direction is going to be 0. Except the car starts to angle the wrong way. Because the car is angling the wrong way, the air friction, effects of air friction is no longer negligible. Air friction actually slows down the car significantly. So the question is, why did the car angle the wrong way? Okay, so one thing that you don't get to say at this point is because the engine is heavy. Just remember, the motion is free fall, only one direction. For relatively heavy objects, the effects of air friction is negligible, so which means that weight doesn't matter. So there's got to be a better explanation as to why the car angled the wrong way.
To you and me, it's a bird feeder. To him, it's a tilt-a-whirl.
Okay, so as this
have to get him
squirrel is getting closer and closer
points for commitment.
to the bird feeder,
He's got to have lost his appetite by now.
it speeds up, right? All right, so as the squirrel starts to get closer and closer to the bird feeder, it's speeding up. How's that possible? Once again, the speeding up implies that it's accelerating. There's a rotational acceleration. The rotational acceleration implies that there is an external torque acting on the system. There's no external torque acting on the system. Okay, no one is pushing the squirrel and make it go faster and faster around the bird feeder. So in the absence of an external force, how is it that the squirrel is getting faster and faster?
Having cleaned the stable of astronomy of circles and spirals, he said, he was left with only a single cartful of dung. He tried various oval-like curves, calculated away, made some arithmetical mistakes, which caused him, in fact, to reject the correct answer. And months later, in some desperation, tried the formula for the first time for an ellipse. The ellipse matched the observations of Tycho beautifully. In such an orbit, the sun is not at the center, but is offset. It's at one focus of the ellipse. When a given planet is at the far point in its orbit from the sun, it goes more slowly. As it approaches the near point, it speeds up. Such motion is
So the Kepler's laws,
why we describe the planets
something that I didn't emphasize before.
as
It's got some important historic.
forever falling towards the sun, but never reaching it. Kepler's first law of planetary motion is simply this. A planet moves in an ellipse with the
Okay, so historically, Kepler's laws are important because it's a step towards Newton's laws. And for whatever the reason, I don't find it very extremely important to discuss it.
sun.
But there's something here that's worth
The
discussing.
ellipse matched the
But the reason why Kepler came up with 3 laws that he came up
observations
with
of Tycho
for planetary motion
beautiful. The sun, the center,
is because of this.
but is
Number one, the planets are not moving in a circle.
offset.
The moon is not moving in a circle either. Orbits are these are elliptical orbitals.
It's at one
Elliptical orbits, more like.
focus of
It's got 2, I'm going to say focuses, foci. And the sun is going to reside in one of the
the ellipse.
focus.
When a given planet is at the far point
So what's happening is when the planet is further away,
in its orbit from the
it's going to be moving at a given speed.
sun, it goes more slowly.
As the planet gets closer to the sun, what happens is it's just going to speed up. And near the sun, it's moving much faster. Away from the sun, it's moving actually more slowly. Okay, the reason why this thing is kind of weird, despite the fact that we're dealing with an elliptical orbit, it's given more or less it's a circular orbit. It's slightly elongated. All right, it's very close to a circle. It's somewhat elliptical, but it's very close to a circle. And you know the gravitational force is acting on it. Notice that the force of gravity is always 90 degrees to the motion itself. So which means that the force of gravity should not be contributing to the motion itself. Okay, so there's no external force acting on the system. There's no external rotational force acting on the system. So there's no reason for these planets to go in faster or slower. Away from the sun, they go slowly. Near the sun, they go much faster. All right, so in order to describe the motion of the planets relative to the sun, Kepler came up with 3 laws of planetary motion.
We made some arithmetical mistakes, which the ellipse matched the observations of Tycho beautifully.
In such an orbit, the sun is not at the center, but is offset. It's at one focus of the ellipse. When a given planet is at the far point in its orbit from the sun, it goes more slowly. As it approaches the near point, it speeds up. Such motion is why we describe the planets as forever falling towards the sun, but never reaching it. Kepler's first law of planetary motion is simply this. A planet moves in an ellipse, with the sun at one focus. As the planet moves along its orbit, it sweeps out, in a given period of time, an imaginary wedge-shaped area. When the planet is far from the sun, the area is long and thin. When the planet is close to the sun, the area is short and squat. Although the shapes of these wedges are different, Kepler found that their areas are exactly the same. This provided a precise mathematical description of how a planet changes its speed in relation to its distance from the sun. Now, for the first time, astronomers could predict exactly where a planet would be, in accordance with a simple and invariable law. Kepler's second law is this. A planet sweeps out equal areas in equal times.
Kepler's first 2 laws of planetary motion may seem a little remote and abstract. All right, planets move in ellipses and they sweep out equal areas in equal times. So what? It's not as easy to grasp as circular motion. We might have a tendency to dismiss it, to say it's a mere mathematical tinkering, something removed from everyday life. But these are the laws our planet itself obeys, as we, glued by gravity to the surface of the Earth, hurtle through space. We move in accord with laws of nature, which Kepler first discovered. When we send spacecraft to the planets, when we observe double stars, when we examine the motion of distant galaxies, we find that all over the universe, Kepler's laws are obeyed. Many years later, Kepler came upon his third and last law of planetary motion, a law which relates the motion of the various planets to each other, which lays out correctly
the clockwork of the solar system. He discovered a simple mathematical relationship between the size of a planet's orbit and the average speed at which it travels around the sun. This confirmed his long-held belief that there must be a force in the sun that drives the planets, a force stronger for the inner fast-moving planets and weaker for the outer slow-moving planets. Isaac Newton later identified that force as gravity, answering at last the fundamental question, what makes the planets go?
Kepler's third, or harmonic law, states that the squares of the periods of the planets, the time for them to make one orbit, are proportional to the cubes, the third power, of their average distances from the sun. So the further away a planet is from the sun, the slower it moves, but according to a precise mathematical law.
Dude.
Having...
This guy. Does anybody know who this guy is? Going once, going twice. Not a single person knows who this guy is.
Richard Feynman?
Richard Feynman. Okay, no. Oh, how do you know
Isn't
Richard Feynman? Go ahead.
Isn't he like Charles Yeager or something?
Charles Yeager. Okay.
I don't know.
I know. I'm okay. Jack Yeager. Okay, I'm gonna give you both of you guys 5 points for whatever it is that you said. Richard Feynman is my hero. He's a theoretical physicist. He's considered to be the best physicist next to Einstein. He's got a tremendous amount of contributions in modern physics, obviously. So this guy's not Richard Feynman. And when you say Yeager, I think that's the guy. I forgot his first name. I'm just gonna say Jack Yeager. He's the guy who broke the. I was gonna say tomorrow record. Broke the sound barrier. All right. This guy is okay. Let me just open up the chat. This is more of a curiosity thing because it's the end of the. Damn, I can't even open that. Okay, so. Okay, Sagan, very good. Jack, give yourself 20 points for that one. Mask magician, no. It's Carl Sagan. This is the original cosmos, late 1970s. Carl Sagan is the first guy in the United States who tried to popularize science. All right, so those of you guys have seen the movie Contact. All right, so he's the author of the novel Contact at the same time. And those of you guys have seen the recent episodes of Cosmos. This guy's the originator of Cosmos. All right, so he's like one of the biggest names in astronomy, astrophysics, physics as well. All right, so the only question that I have is, I'm asking the same question time and time again.
From the sun.
Notice that when you bring the mass closer to the
it goes more slowly. As
it speeds up.
Approaches the near point,
when you move the mass away from the corner of rotation,
such
it slows down.
Motion is why we describe.
All right, I've been asking the same question time and time again.
The planets.
Using different examples. So the question is one. All right, so we briefly talked about torque the week before. If the rotational force or force acting on this mass is going to cause it to accelerate, except notice that this mass is attached to this pivot that you're looking at. So this becomes the axis of rotation. So there's going to be a torque acting on it in that direction. Okay, so I'm going to take you through the derivation. So this force acting on this mass is rigidly attached to this point. So as a result, this mass is going to experience a torque or rotational force. Okay, force is your linear expression. When you take a linear expression multiplied by the radial distance, it's going to give you your angular expression. So something that we're playing with previously. So force times its radial distance with respect to the point of rotation is going to give you the rotational force or the torque. So what if the force is coming at an angle? Okay, so we will express the angle, measure the angle with respect to the radial direction. So the force, which is component of the force, which is parallel to the radial axis, is the parallel component. So F double bar is the parallel component. The force, which is responsible for the rotational motion, is going to be the tangential component of the force. So it's going to be tangential to the curve of motion that you're looking at. So tangential component of the force, when you make it a small triangle, it's going to be the opposite of the hypotenuse. So the opposite is going to be the sine of the angle of the force that we're looking at. All right, so back substitution. It's going to give us a generic equation for the torque. So the tangential force is going to cause a tangential acceleration. Tangential acceleration can be expressed in terms of the rotational acceleration. Do a back substitution to that one. All right, so you have R and R, so it's going to give us mr squared. So mr squared. So this is our rotational force. This is our rotational acceleration. So mr squared is going to be our rotational mass. All right, so it becomes alpha, F becomes tau, and M becomes mr squared. So that's our rotational mass, like term, or moment of inertia, or rotational inertia. So the rotational inertia is going to depend on mass, and the mass is radial distance to the point of rotation squared. All right, so that's the generic expression that we will get to use. So for torque, this is one of the formulas that we will get to use. All right, so mass-like term is going to experience acceleration, and that's going to give us the rotational force. So rotational force acting on the rotational inertia is going to cause it to accelerate rotationally. Okay, so what else do we have here that I'm interested in? Nothing. Okay, so let's move forward. Okay, so let's build on this expression. All right, so for our purposes in this chapter, okay, we will always have a pivot. Pivot is going to be a point of rotation. Force is going to be acting at a given distance, a radial distance. If the force is coming at an angle, angle is going to be measured with respect to the radial direction. So that you can break the force into two components. There's going to be a parallel component of the force. There's going to be a perpendicular component of the force. So the perpendicular component of the force is going to be responsible for the torque. That's what it says. And the perpendicular component of the force is going to be sine of the angle of theta. So it gives us a generic expression. And so the torque is going to have a direction. Counterclockwise direction is going to be positive. Clockwise direction is negative. Problem number 3 from the handout, simple demonstration problem. So you guys know how to use it. So what we got the axle. We're looking at the wheel, axle of the wheel. It's going to experience 3 forces acting on it. So the question is, what is the net torque caused by these 3 forces acting on the axle? Okay, so this becomes my first force. So this is the first radius. The inner radius is going to be 12 centimeters. And this is F1, the first force. So it's going to be 35 newtons. All right, so the outer radius is going to be 24 centimeters. All right, so this is the radial distance to this force. It's the same radial distance to this force as well. All right, so the second radial distance is going to be 24 centimeters. I'm going to label this as the second force. The radial distance is once again 24 centimeters. Notice that I'm also going to label this one as the third force. All right, so that's 18 newtons. All right, so this is going to be R2. This is going to be R3. Both of them are 24 centimeters. Okay, so I labeled everything. So the question is, what is the net force? Centimeters need to be expressed in terms of meters. So move the decimal to the left by 2 decimal places. So the net torque means that just add up individual torques. All right, so let's figure out the individual torques. All right, so torque due to this force is going to be this force times the radial distance and times the sine of the angle in between. Okay, guys, the sine of the angle in between is the angle is going to be 90 degrees. Sine of 90 is going to be 1. So this is going to be R1 times F1. This force is going to cause a clockwise rotation. So the clockwise rotation is going to give you a negative torque. So T1 is going to be, tau 1 is going to be negative. All right, so there's a second force here. This force is going to be responsible for the torque in the counterclockwise direction. So that's going to be a positive torque. So it's going to be R1. No, this is going to be R2, which is 12 centimeters, times F2, times the sine of 90 degrees. Sine of 90 degrees is going to be 1. So that's going to give us a positive rotation. So it's going to give us a positive rotation right there. All right, so that's a positive torque. Okay, now let's focus on the torque, which is going to be caused by the third force. So the lever arm is here in this direction, radial distance. Force is 90 degrees to it, so sine of 90 is going to be 1. So this is going to be R3 times F3. And it's causing, this one is causing a clockwise rotation, so this is going to be negative. It's going to be a negative torque. All right, that's it. All right, so now write out the expressions for torque. The first torque is going to be R1 times F1. The second one is going to be R2 times F2. The third one is going to be F3 times R3. All right, so what do we have? R2 and R3 will be the same. All right, so we will factor those out. And that's it. So that's the final equation. Okay, so plug the numbers in. And then we're done. All right, so we end up getting a negative torque. Negative torque is going to be in the clockwise direction. All right, so this is going to be a negative torque. I must have been getting tired, so I made it positive, but this is the negative torque. All right, so let's talk about rotational work, because this is one of the concepts that we will get to utilize shortly. All right, you can get it rotational work from linear work. All right, number one, you have to go back to the definition of work. The work is a process of transferring energy. You do transfer energy by combining force and its displacement. But if the force is on the direction of displacement, it's going to add energy to the system. So which means that if the force is responsible for this motion, it's going to increase the kinetic energy of the system. If the force is opposing motion, it's going to reduce the kinetic energy of the system. All right, so how do you go from linear work to rotational work? So now that we got this formula, what we do is force becomes the rotational force, the torque. Displacement becomes the rotational displacement. Changing kinetic energy is going to become the change in rotational kinetic energy. So this formula could be reformulated in terms of that formula. So this is called the angular work. All right, visually, it kind of looks like this. I'm going to move this mass in this direction. I'm going to rotate this mass in this direction by applying a rotational force on it. By applying a rotational force on it, I'm going to displace it in that direction. So which means that I'm doing rotational work on it. So what happens when I do rotational work on it? What happens is its rotational speed is going to increase in that direction. So it's going to undergo a rotational acceleration in that direction. So notice that you got the initial rotational velocity, and then it's going to increase in that direction. So that's what changing rotational kinetic energy means. Its rotational velocity is increasing. All right, so the topic of this week's discussion is
To you and me, it's a bird feeder. To him,
the angular momentum.
it's a tilt-a-whirl.
All right, so notice that as it's bringing its mass closer to the point of rotation, it's speeding up. All right, the question is why? The short answer is because of the conservation of angular momentum. And so what's the meaning of angular momentum, and how do you conserve it? Okay, guys, we will play the same game. Okay, so we will take linear momentum, regular linear momentum. Momentum means motion. So mass is moving at a given velocity. That's your momentum. All right, if this mass is rigid attached to a pivot point, a point of rotation, what happens is this momentum becomes angular momentum. So you find the momentum of the system. Linear momentum of the system is going to be mass moving at a given velocity. So P is our momentum. And then you take this linear term and multiply by the radial distance to the point of rotation. It's going to give you the angular momentum. All right, so this is the tangential momentum in a sense that it's following the curvature of the motion times the radial distance is going to give you L. L is the angular momentum that we're looking at. All right, so let's expand on this. Let's check to see how many different formulas that we could come up with which are useful. All right, so P is mass moving at a given velocity. All right, I'm going to keep this expression the same. I'm just going to move mass up front in order to come up with the standard expression for angular momentum. This velocity is the tangential velocity. It could be expressed in terms of the rotational velocity, so we'll do a back substitution. R times R is going to be R squared. MR squared is going to give us the rotational inertia. All right, so which is the generic expression for it. And then we're done. Okay, so P becomes L. P is the linear momentum becomes L. Mass becomes the rotational inertia. And V becomes W in essence. Okay. Now, there are two expressions for angular momentum. This is the linear expression expressed in terms of tangential velocity. And this one is expressed in terms of the angular velocity. Okay, both of them are just as useful. Okay, so we will switch between these two in expressing ideas. So this represents angular momentum. So what conserves angular momentum? What conserves angular momentum is the absence of an external torque. All right, so in the absence of an external torque, in the absence of a rotational force acting on the system, the angular momentum of a system is going to be constant. All right, so what conserves angular momentum is the absence of an external force. So the conservation of angular momentum is initial and the final angular momentum will be the same. Okay, once again, angular momentum could be expressed in terms of the rotational velocities as well as the tangential velocities. All right, so the either expression is going to work. So
You and me, it's a bird.
from our vantage point, what does that mean? Okay, so what that means is angular momentum of the system is going to be constant, so it's not changing because there's no external force acting on the swirl. Nothing is pushing it, making it go faster or slower. The other thing which is happening is swirl is bringing its mass closer to the point of rotation, and when the swirl brings its mass closer to the point of rotation, it's simply speeding up. So the question is why? It's initialized within this formula. So this is the mass. This is the radial distance of this mass to the point of rotation. This is the speed of this mass that we're looking at. So remember, the angular momentum is going to be constant because there's no external torque acting on the system. When you bring this mass closer to the point of rotation, what happens? It's going to speed up. Its speed goes up. When you pull the mass away from the point of rotation, it's going to slow down. So because the angular momentum is constant, which is the conservation of angular momentum, when you move the mass further away from the point of rotation, this motion is going to slow down. When you bring the mass close to the point of rotation, it's simply going to speed up. That's it. All right, that's the entire crux of the lecture. Earthquake. The Earth ended up speeding up because the radius of the Earth shrunk by 6.7 inches. The Earth ended up speeding up. As a result, we end up losing 1.8 microseconds a day. This is the conservation of angular momentum. When you bring the mass closer to the point of rotation, it simply speeds up because the angular momentum is conserved.
My name is Mike Fossum. I'm the commander of Expedition 29. Welcome to the International Space Station. You may wonder why the International Space Station doesn't tumble in its orbit around the Earth. Well, we have a system that maintains our attitude control system, if you will. There's really two ways to do this, to approach it. The first way would be to use rockets or small jets that would keep thrusting and pushing to nudge the space station into its correct attitude. Problem with using thrusters like that is it requires a lot of fuel that we have to continually ship up from the Earth. So instead, we use angular momentum and gyroscopes. Let me demonstrate a little bit. Before we get into this, we really have to talk about the definitions of the concepts. It's really the conservation of angular momentum that's really important here. I have this flashlight rotating. In physics, this angular momentum of an object rotating about some reference point right here in the middle, that's a measure of the extent to which the object will continue to rotate around that point unless it's acted on by an external torque. Now, torque has to do with the ability of a force to rotate an object and how far away from the center that force is applied. The angular momentum of a single rotating body is equal to the product of its rotational inertia, that's just physical properties of the mass distribution, the rotational inertia, and angular speed, how fast is it moving. The angular momentum and rotational inertia, that includes the mass, are constants in the system. Angular momentum of the system remains constant if no external force is acting on the system. This is the law of conservation of angular momentum. I can demonstrate this to you with me actually doing a little bit of a demonstration here. So I want you to watch this. I'm going to have to unclip the microphone or I'll tie myself up in knots. Again, what's going on as my body spins doing this and moving my arms in and out from being close to the body is when I bring the arms in closer to the body's rotational inertia is decreased. The angular momentum must be conserved. As the rotational inertia is decreased, the angular speed increases and vice versa. This is called an inverse relationship. Now, no external force acts on the system, and thus the angular momentum about the axis must remain the same. My name is Mike Fossum.
Law of conservation of angular momentum. Now, that law says that the angular momentum of a system remains constant unless the system is active.
Okay, so angular momentum is going to be constant in the absence of an external torque. No one is there just pushing him and making him go faster or slower. All right, so when he spreads his arms out in that direction, he's increasing his moment of inertia. Okay, now we're looking at things from a different perspective. We're using the rotational motion equation for the angular momentum. All right, so he's moving the mass away from the point of rotation. So by moving the masses away from the point of rotation, he's increasing the distance on the side of the rotational axis. So he's increasing his moment of inertia. As soon as he increases his moment of inertia, the rotational speed goes down.
What I was demonstrating was the law of conservation of angular momentum. Now, that law says that the angular momentum of the system remains constant unless the system is acted upon by net external torque. Now, angular momentum is the product of an object's rotational inertia and its angular velocity. What I was doing by moving these masses in and out was changing the rotational inertia of my body. With the masses out, a fair amount of mass was distributed far from the axis of rotation, which was a vertical line passing through the center of my body and right through the stool. When I brought the masses in, I decreased the rotational inertia. Now, the angular momentum is the product of the rotational inertia and the angular velocity, and that remains constant as long as we don't have a net external torque. So at the beginning, I had a large rotational inertia and a relatively small angular velocity. When I pulled my arms in, my rotational inertia went way down, and my angular velocity went way up in order to keep the product of the two a constant.
So if you increase the rotational inertia, the angular velocity is going to go down. If you reduce the rotational inertia, the angular velocity is going to go up.
Now let's look
Only if the angular momentum is constant.
at this again with me holding two masses in each hand. This is going to give me a greater change in rotational inertia.
Why does that give him a greater change in rotational inertia?
There you can see that the changes in my angular velocity were greater because of the greater change in rotational inertia. Now, we've been saying that the law of conservation of angular momentum applies as long as no net external torque acts. In fact, there is a net external torque on the system, you can see, because as the stool rotates, it will slow down because there's friction, which is exerting a torque on the axle. But this is small enough that you can still see the changes in angular velocity that are affected by the changes in rotational inertia. This is an effect that is used to good advantage by ice skaters in the high velocity spins that they achieve. They start their spin fairly slowly, but then they bring their arms and legs in very tightly, and that makes them spin at a very high rate. Law of conservation of.
And so how's that possible? All right, so in the absence of an external torque thing on the system, when you extend your arms like that, it's going to increase the moment of inertia. As a result, angular velocity goes down. When you bring your arms and legs in, that's going to reduce the moment of inertia. As a result, the rotational velocity is going to go up. Okay, guys, take a break for 10.
Okay. All right, let's go over that a little bit.
To compete at the highest levels, skaters must perform a series of jumps.
Very secure and very balanced.
The most difficult is the triple axel, which involves 3.5 turns in the air.
The hardest part is to transfer your weight over that right side at the right time and straight. And get the feet in fast. Don't take a long time to get from there to there, and make sure that the feet and ankles are tight.
Kathy Casey is coaching Damon Allen, who is ranked 5th in the nation. Her goal is to help him master the jump.
When I began skating, the triple axel was kind of like, a few people had accomplished triple axel. And now triple axel is like, if you don't have triple axel, you might as well just go back home, pack your bags, and get back on the plane.
The triple axel did not appear in competition until recently. Several years ago, on a world tour, Casey and her skaters were taken by surprise.
People who I considered weren't so very talented from Russia were doing triple axels. And I said, those Russians know something we don't know, and I think we better try to catch up with them if we can.
Casey believed the science of biomechanics would reveal the answer. At her request, sports scientists from the Olympic Training Center brought their cameras to her rink to analyze the jump.
Kathy Casey came to us and asked us to do a study on the single, double, and triple axels. How long does it take a skater from when he leaves the ice to reach his rotating position? Is the triple axle higher than the double axle, or are the skaters just rotating faster? Those are quantitative variables, which you can't get just from watching the jump. They have to be measured.
To understand the jump, it had to be translated into mathematical language, a job that would take Deborah King and her colleagues many months to complete.
You have to analyze each tape one jump at a time. We pause at each frame, and we mark the head, each shoulder, the hips, the elbows, the wrists, pretty much all the major joints of the arms and legs. You repeat that for the next camera view, and then you calculate the three-dimensional coordinates of all the joints of the skater for that one jump. And then once you have those three-dimensional coordinates, you can basically reconstruct the jump on the computer.
With each jump reduced to numerical coordinates, King could now begin to answer some questions.
These skaters cannot disobey the laws of physics. Like what goes up must come down. How fast they're going right instant of takeoff is going to determine how high they jump. And then basically you use different mathematical techniques incorporating these laws of physics to find out the answers.
To understand the choreography of the jumps, King needed to learn how skaters use each limb to execute them. Using geometry and trigonometry, she connected joints to form angles to measure the position of arms and legs. The video camera, which recorded 60 frames per second, was used to measure time. Plotting the location of each joint from one frame to the next, King could use calculus to see how the skater's body parts changed throughout the jump. With statistics, she could then determine how the single, double, and triple jumps were different. The question was whether to jump higher or spin faster.
If you do your very best jump, very best single, your very best double, your very best triple, they're all going to be the same jump height. So the way they're getting the added rotations is really getting into their rotating position more quickly. We presented the results to Kathy, and we gave her all these graphs and sat down with her. And basically she told us she had absolutely no idea what any of that meant.
I said, guys, we're in kindergarten. We're not PhD majors in biomechanics. We're in kindergarten. You have to make it so that skating coaches and skaters who haven't studied biomechanics understand this.
So we went and tried to learn a little bit about figure skating vocabulary, and she worked to understand a little more about science and math. And once we were communicating, it took off, and she's really excited with the results.
We did find out that you're not in the air any longer, which is amazing. That's very, very interesting. You're not in the air any longer.
Before the study, we believe that you need to throw your leg out further for a triple. In reality, it needs to be closer, so you can get into the air and into your rotation much quicker.
That was better. Let's go over that. All right, ready? Step up, quick, out quick. Good. All right, you got to remember, you got to stay in, and don't anticipate the landing toe right before, and then be much quicker. We found out that the people with the strongest arms did better triples because it was who could pull in quick and tight with their arms that made that extra rotation. Okay, good.
Damon and Allen, 21 years old. I'll let us swim. That will go. And a wonderful back headless spin. This is the moment that's a complete rush to know you skated your best.
An athlete takes his performance to new heights. Skating is one of many sports where mathematics is helping athletes to push their limits.
Okay, so does the jump height matter?
No.
Okay, it does matter, but there's not much difference between a double axle and triple axle when it comes to jump height, right? Okay, so quad is obviously it's 4 rotations. So the jump height is not the most important thing when it comes to triple axle, double axle.
Physics of how Gable's body moves inches off the ice and be completed.
Right, so 21 inches is what you need.
Jump height is the second element. That's not high for Gable, only 21 inches off the ice. Third and most critical, moment of inertia. The spin has to begin immediately, and to do that, arms and legs have to be tucked close to the body. The physics of how Gable's body moves through the quad.
Okay, so a couple of things which are important. Obviously, 21 inches, you should be able to jump that high. It's not that much of a height.
Immediately, and to do
you need to have narrow shoulders.
that, arms and legs.
You need to be extremely thin.
Legs have to be tucked close to the body.
Okay, so women have narrow shoulders. They can be thin, so it's not a big deal. Okay, so you need to be as thin as possible. You need to have as narrow shoulders as possible so that you can tuck all this mass into as close to the point of rotation as possible.
The physics.
The most important thing is strength.
Of how Gable's body
the
moves.
stronger you are, the faster you can pull in your arms and legs together as tightly as possible, the faster you will spin.
Through the quad.
So the strength is the most important thing.
Amazing.
And with training, women should be able to do the same.
Biomechanics expert Jim Richards.
He swings everything around. There it all uncoils, but as soon as he leaves the ice, the best part of it is how tight his arms are in.
And to achieve that spin rate is to bring everything together.
Everything's
It's stronger you are, the faster you're going to be able to pull your arms and legs in.
as tight as possible. What that does is it maximizes the rate of spin.
Richard says women don't do quad jet because they don't jump high enough.
Well, that's not the reason why. Okay, problem number 1. Okay, this problem became available because. Okay, so not only is this a good demonstration problem, but also there's a great deal of physics that is interesting here. Okay, so problem number 5. So what do we have? We got this figure skater is increasing her spin rotational rate from half a revolution per second to 3 revolutions per second by changing her moment of inertia. So she's reducing her moment of inertia in essence. Right, so in terms of the demonstration problem, there's not much here. So this person is going to go from half a revolution to 3 revolutions per second, reducing her moment of inertia. So notice that the rotational speed goes up by 6, which means that her moment of inertia has to go down by 6. Revolutions per second needs to be expressed in terms of radians per second. There's no net external torque acting on her. No one is pushing her in the direction of the spin, so angular momentum is going to be constant. We'll express the angular momentum in terms of the moment of inertia as well as the angular velocity. So let's take a look at what happens to her final angular momentum, the angular rotational inertia. So her rotational inertia goes down when she pulls her arms in. It's 6 times smaller. As a result, her speed is going to be 6 times larger. Okay, part A is a straightforward textbook physics problem. Okay, this sort of stuff bores me kind of silly. You guys kind of need it. It's just there's not much usually takes place. You kind of see the way the concept is being used in a silly sort of way. The stuff that I'm interested in is part B. That's the stuff that I came up with. What happens to her rotational kinetic energy? So this is a lot more interesting than part A. Part A is this is how you use the formula. So what happens to her rotational kinetic energy when she pulls her arms in? What happens when she pulls her arms in? Obviously, her moment of inertia is going to go down. Her rotational speed is going to go up. You're thinking that because there's no net external force or torque acting on the system, there's not going to be any change in rotational kinetic energy. And that's the way conceptually I would look at it. When you plug the numbers in, though, all of a sudden you realize that she gains rotational kinetic energy. So her rotational kinetic energy goes up. How's that possible, guys? There's no external force feeding energy into the system. There's absolutely no external force feeding energy into the system. There's absolutely no external torque feeding energy into the system. Yet her kinetic energy, rotational kinetic energy goes up. Where does that extra kinetic energy come from, if that's the case? I mean, we know that her angular momentum of the system is constant in the absence of a net external torque acting on the system. So there's no external work being done on the system. Only through work you can transfer kinetic energy, but there's no work being done on the system by an external force. So how is it that her kinetic energy is increasing? Who's got the answer for that question? I guess that's a bit of a mind twister. If you got the answer, I'm going to give you 20 points for it. How does she increase her kinetic energy? She increases her kinetic energy by pulling her arms in, right? Arms as well as the legs in. So where do you suppose the energy is coming from? Energy is coming from
angular momentum?
No, it's not the angular momentum. Where's the energy coming from, guys? It's coming from her body, right? She's part of the system. So what's happening is there's no external force feeding energy into the system. What's happening through the internal forces, her chemical potential energy gets converted into heat, and then it gets converted into the motion of her pulling her arms in and legs in, and that gets converted into the rotational motion. All right, so you end up getting a conversion process. All right, so what appears as the increased kinetic energy comes from the conversion process of her the chemical potential energy getting converted into the rotational kinetic energy. All right, so there's no force feeding energy into the system external. It's just what happens within the system. What happens, the conversion process takes place. All right, so just for the hell of it, because I was curious about it. So changing rotational kinetic energy. All right, so not only your rotational velocity is changing, but also the moment of inertia is changing. All right, here's the final moment of inertia. Okay, I'm going to express the final moment of inertia in terms of the initial moment of inertia. So the initial moment of inertia is going to be common to both of them, so you can factor that out. And then you end up coming up with this expression, which is kind of weird, because if your final angular velocity is larger than the initial one, which means that you're getting kinetic energy. If it's smaller, which means that you're losing kinetic energy. All right, this is more of a sample problem number 6. All right, so this is, once again, related to a skater. This person is spinning at 3.5 revolutions per second. With her arms close to her body. So what's her angular momentum at that moment? Okay, so this is the case that we're looking at. So she's just spinning. And then how much torque is required to bring her to a complete stop? So this is problem number 6. All right, so initially she's spinning at a rate of 3.5 revolutions per second. This is her height expressed in terms of meters. All right, so we are assuming that she resembles a uniform cylinder, the radius of 15 centimeters. All right, so we're using an approximation. So she's got weight, her mass is 55 kilograms. All right, so we got 2 conversions, centimeters to meters, and revolutions per second to radians per second. Okay, so find the angular momentum, and then figure out the amount of torque required to bring her to stop within 5 seconds. All right, so this should be radians per second. Okay, so we got the conversions now. All right, so for angular momentum, obviously we got this formula. You can either take the rotational velocity term or the tangential velocity. It makes sense to use the rotational velocity because we got the initial rotational velocity there. All right, so the rotational inertia, we make the assumption that she's going to resemble a uniform cylinder. So we use 1/2 mr squared for that. Do a back substitution. I think that's as far as this goes. So the rest is just plug the numbers in and get a number in terms of the proper units. All right, so what's the amount of torque required to bring her to stop? So we got 2 torque equations. Either we use this one or that one. It makes sense to use this one because we already know what the moment of inertia is. Also, we're using the angular terms. So use the same moment of inertia for this cylinder, solid cylinder. Alpha is the angular acceleration. So either it's the angular average acceleration or uniform acceleration. I would use the uniform acceleration. So as to which formula to use, you know the initial velocity, 3.5 revolutions per second. We know the final velocity. All right, we also know the time. So it makes sense to use that one. Isolate the alpha from there. And then back substitution. Okay, so we end up getting negative torque. Okay, this implies that obviously negative means that it's pointing in the opposite direction of the initial angular velocity. So it's going to be opposing the initial angular velocity. So you plug the numbers in. Okay, so the negative torque means that the motion is going to be in the clockwise direction. But the torque is going to be in the clockwise direction. All right, so you can come up with a second solution. All right, so the force is how fast the momentum changes in time. All right, so we can go from a linear expression to an angular expression. Force becomes tau. Momentum becomes angular momentum. All right, so this is how fast the angular momentum changes in time. All right, so you go from an initial angular momentum to a final angular momentum. Actually, the final angular momentum is going to be 0, not the initial one. All right, so this is what happens when you're preparing a lecture late at night. This idea is the same, though. All right, so here's the change in momentum. This is going to be negative in essence. The time is going to change within 5 seconds. All right, and then obviously this is going to be negative. So because it's negative, you end up getting a negative number.
And you curl it in the direction of the spin, you really quickly just pull the wheel. You could do it. So I would probably do it like this. So both hands in this direction. I'm going to get it spinning.
Okay, in the absence of a net external torque acting on a system. Okay, so I'm giving you a generalized expression for it. The total angular momentum of the system before and after any variation within the system is going to be conserved.
And then you're just going to rotate it. Essentially.
So the total angular momentum before he rotates it and after he rotates it is going to be
eventually all the way upside down. Okay, so hold that.
So the system is going to be, system involves a rotating wheel and a person.
I would hold it that way probably. Are you comfortable in the chair? Yep. All right, I'm going to have you hold the shoulders because I'm going to have to.
All right, so this is also going to be a rotating chair.
Just to get this rotating. Actually, that's probably okay. Let go. No.
Let go. So the angular momentum of the system is going to remain constant at this point. So there's a net angular momentum of the system. The system is composed of a rotating wheel and a person on a rotating chair. And then
rotate the wheel.
When you rotate
all the way over.
Angular momentum of the system is still the same. It's still going to be constant, except as soon as you rotated the wheel in the opposite direction, and it's a rotating wheel. Notice that some of that rotational motion got transferred to him. Now his body is moving in the opposite direction of the rotation of the wheel.
And if you go back the other way, you should stop because now all the angular momentum is on the wheel again. And stop. Sure, and you go all the way up, and then go this side. There we go. Anyone else?
All right, so that's the conservation of total angular momentum. All right, so the conservation of total angular momentum involves a system of interacting masses. Why is this vehicle falling short? Why is it that it's not going all the way down there? The reason why it's not happening is because the car starts to angle the wrong way immediately. The reason why the car is angling the wrong way is because this driver put the brakes on. He was probably told not to do that. Reflexively, he puts the brakes on because he knows he's going to be landing on top of these cars, and then he's just preparing himself. He wants to hit the cars with his brakes on. The problem with that is when the wheels are rotating, this car, the vehicle, and the tires, the vehicle, this combination, this system has a total angular momentum at that point. So the total angular momentum of this system is going to remain the same before he engages the brakes and after he engages the brakes. As soon as he engages the brakes, the tires will stop spinning. So what happens to rotational motion? It gets transferred to the mass of the car. The car is going to slowly will start to turn. All right, so that's the conservation of total angular momentum.
Bart, do you have your slingshot?
No, sir.
I see it in your back pocket.
Just don't stretch it out.
I was once a boy, and like all boys.
You like all boys?
Shut up! A child is in danger under my aegis. Run, Ralph, run!
Okay.
Time to do what I've never done as principal. Something.
Skinner's spazzing out!
I'm not spazzing out. I'm using the principle of conservation of angular momentum to turn the container.
That is so cool. That's the kind of stuff they should teach in school.
We do teach it in school. You're too busy eating sugar snacks and horsing around.
He's right. Learning can teach you things. Education rules.
So that's the conservation of angular momentum. So he jumps on the container, and total angular momentum of the system, and the system now consists of the principle of running on top of the container and the container itself. As soon as the principle starts to run in the counterclockwise direction, the container is going to start to spin or rotate in the counterclockwise direction. As a result, the total angular momentum of the system is still 0.
For decades, the Winter Olympic Games has drawn people from across the world to marvel at breathtaking athletics on the snow and ice. One of the most popular events is figure skating. Athletes meld acrobatics, dance, and physics into mesmerizing performances. It is the sheer precision that separates the skilled athlete from the novice. Through years of tireless training, skaters must learn to understand and use angular momentum to become the best in their sport. Angular momentum is the product of a skater's moment of inertia and angular velocity and is represented by the letter L. When a skater is rotating with no net external torque acting on her, angular momentum is conserved. With her arms and leg outward, she increases her moment of inertia, which reduces her angular velocity. As she pulls her arms and leg inward, she is able to spin faster since her angular velocity increases while her moment of inertia decreases. And this is how skaters become champions.
Force is what causes acceleration. Torque is the rotational force. So F becomes tau, mass becomes rotational mass, T becomes alpha, rotational acceleration. All right, so write down the torque for the following setup. We're interested in the component of the force which is going to be perpendicular to the radial axis. All right, so that becomes sine of the angle of theta times F. So the torque is going to be caused by the tangential force or the perpendicular force times R. So end up getting that formula. Torque is positive when it's in the counterclockwise direction, negative in the clockwise direction. Work is force causing displacement or opposing displacement. Rotational work is the rotational torque causing rotational displacement or opposing rotational displacement. Momentum is mass moment at a given velocity. Your momentum is the same expression in terms of the angular components. What conserves momentum is the absence of an external force. What conserves angular momentum is the absence of an external torque acting in a system. So what happens to angular velocity if the moment of inertia is suddenly reduced? So the moment of inertia goes down, angular velocity is going to go up. Okay, guys, there's a typo. It should be suddenly increased. So what happens to the angular momentum if the moment of inertia is suddenly reduced? All right, that's not true. Okay, question number 14. What happens to the angular velocity if the moment of inertia is suddenly reduced? What happens to the angular velocity if this moment of inertia is suddenly reduced? Is the angular velocity is going to go up? Okay, evidently I didn't read this question carefully. And I assume that what happens to the angular velocity if the moment of inertia is suddenly reduced? That's not what it says. What happens to the angular momentum if the moment of inertia is suddenly reduced, guys? Nothing. Angular momentum is going to remain the same. All right, so evidently I'm not reading it carefully, so moving forward. What happens to the rotational kinetic energy when the moment of inertia is suddenly reduced? Your momentum is not going to change, but what happens to the rotational kinetic energy is going to go up. So where does the actual kinetic energy come from? The moment of inertia is suddenly reduced. It comes from your muscles. it gets converted from the stored energy in your muscles in the form of chemical energy into the rotational kinetic energy of your motion. Okay, so squeezatron. All right, so you pull this up, it's going to bring the masses near the point of rotation. So when you bring the masses near the point of rotation, what's going to happen? Your momentum is going to be constant, so it's going to speed up. We kind of knew that. Okay, the stuff that I'm interested in is the Kepler's observation, which is the planets are further away, they slow down, further away from the sun, they slow down. When they're near the sun, they will speed up. Once again, this is the conservation of angular momentum, conservation of total angular momentum. All right, so when you increase the radial distance, what happens to speed? Tangential speed is going to go down. When you reduce the radial distance, the tangential velocity is going to go up. All right, so that's the principle of conservation of momentum. Explains that.
But despite this legacy of engineering, cascades often fall victim to the forces of gravity. Luckily, serious injuries are rare, and only one person has died in the last 100 years. When a tower falls, cascaders have a word for it. They call themselves yenya, or firewood. Each group has their own rehearsal building, where they practice year-round. The towers are carefully mapped out before the first foot is put into place. The towers range from the simple to structures that can reach up to 9 stories high and contain as many as 300 people. More than 30 groups from different provinces face off in the country's various competitions. On tower building days, participants wear traditional folk dance costumes, white trousers, and brightly colored shirts. The most essential piece of clothing is the sash that's wrapped around the waist of each participant. This provides back support, as well as critical foot and hand holds. Over the cheering crowd, the human tower begins to take shape. A majority of the cascaders, sometimes numbering into the hundreds, form the base. They're the strongest members of the tower and call themselves squatters. Lighter people make up the center of the human pillar. As a tower builds, the pressure mounts. One wrong move can send the entire group crashing to the ground. Nine-story falls notwithstanding, a successful cascade is always crowned by a fearless child who scrambles to the top of the heap.
From Olympic champion Evan Lysacek.
Imagine what it's like to hurl your body in the air and rotate 4 times.
To Olympic hopeful Ashley Wagner.
This is what I've been working for my entire career.
Figure skaters push themselves through incredible jumps, spins, lifts, and throws on ice and make it look elegant and effortless.
From your starting position to your very last movement, and even the way you get off the ice, every detail counts.
Making the difficult elements look effortless takes exceptional artistry, athleticism, and a solid understanding of some basic principles of physics.
There's no better example of physics than on an ice skating rink, with a wonderful place to see science. T+5.
Brad Orr is the head of the physics department at the University of Michigan and has been funded by the National Science Foundation. Orr explains that good balance or stability is basic to everything a skater does, and that begins with an understanding of the center of mass, the balance point in which an object's mass is concentrated.
This is easiest to see in a completely symmetric object like a basketball. The center of mass is at the center of the sphere. As you get to objects which have less symmetry, it's a little harder to figure it out, but it's still the center of where the object is.
The center of mass for a figure skater is usually in the hip area, well above the feet, or point of support.
But here we come to a situation which is unstable, and this is what the figure skater actually has. Her center of mass is up around her hips, and her skates are touching the ice down here.
A figure skater's center of mass must be kept directly above the point of support to
We can't hear you.
2 things which are important in terms of balance: your location of your center of mass and where your center of mass is with respect to the point of support.
maintain balance.
All right, so you need to line up 100%, or else you're not going to be able to maintain your balance.
Adjusting as positions change. This becomes even more challenging in pair skating and ice dancing, which require that both skaters keep their centers of mass over the point of support through lifts, throws, and complicated positions.
So your center of mass needs to be just over
We like to focus
the point of
on
support. Case in point. So the center of mass of the system is located right over the point of support, which is located right here. So this system is in equilibrium as a result. Speaking of equilibrium, there are three kinds of equilibriums. You got neutral, unstable, and stable.
Energy and therefore the object.
All right, let's talk about neutral equilibrium.
This is an example of something that has neutral equilibrium. When I take and I displace the
so the center of mass of a ball is located right at the center of its geometry.
object.
All right, so when you displace it using a force, notice that the center of mass moves translationally, but it does not go up or down. So it doesn't gain any potential energy, or it does not lose any potential energy. So its potential energy remains constant. Because its potential energy remains constant, it's known as neutral.
The center of mass does not go up, therefore it does not gain gravitational potential.
So the center of mass is not going to gain or lose gravitational potential energy. Because it doesn't gain or lose gravitational potential energy, it's known as neutral equilibrium.
Right. That is neutral equilibrium. This is unstable equilibrium.
All right, so the center of mass is located here somewhere. As soon as you displace it from its equilibrium position, what's going to happen is the center of mass is going to lose its potential energy. So the potential energy is decreased. So that's going to give you unstable equilibrium. As soon as you displace the object from its equilibrium position, it loses potential energy, or its center of mass loses potential.
Right? If I displace it from its equilibrium position, it will decrease the gravitational potential energy and therefore fall. This is stable equilibrium.
Right, so this will be stable equilibrium because when it tries to displace it by applying a force, notice that its center of mass just rises up. It gains potential energy. And when you let it go, it loses that potential energy. So it gains potential energy when you apply a force. As soon as you let it go, it loses potential.
When I displace it, the center of mass actually goes up and the gravitational potential energy
so that's going to give you stable
increases. Now notice that this is only stable to a certain point, right? So in order to get something that looks like that.
If a body remains stationary in its position, we say that it is in equilibrium. When we move this ball slightly to one side, it will remain in the new position.
All right, so it's neutral equilibrium. The center of mass does not gain or lose potential energy.
We say that the ball is in neutral equilibrium. When we move a ball along the surface of a hemispherical bowl, forces will appear.
All right, in this case, when you move it if you displace it from its equilibrium position, it loses potential energy. So that gives you an unstable equilibrium.
Forces will appear that tend to make the ball move farther away from the position of equilibrium. We can therefore say that a ball on the top of a sphere is in unstable equilibrium. When we now move the ball slightly to one side, forces appear that will make the ball return to.
All right, so in this case, you move the ball from its equilibrium position, you displace it. Displacing it, you're increasing its gravitational potential energy. You're increasing the gravitational potential energy of its center of mass. So what happens is, as soon as you let it go, it reduces its gravitational
position of equilibrium
while restoring itself to its position of equilibrium. So this is known as the stable equilibrium.
The body remains station of stable equilibrium.
All right, so those are three cases of equilibrium, but what's the condition, or what are the conditions for equilibrium? So one example of equilibrium is tug of war. Each group of people will apply a force in one direction. Those people will apply a force in the opposite direction. The net force acting on the system is zero. It's going to remain zero for a long time. So that means that one condition of equilibrium is the horizontal net force is going to be zero. All right, and this book is in equilibrium because it's got two forces acting on it. Gravity is pulling the book in the downward direction. The normal force is the reaction force acting on the book from the surface. These forces are equal to each other in opposite direction, so which means that the net force acting on the system is zero. All right, so that's the first condition for equilibrium. The net force acting on a system, any given system, has to be zero. That's not the only condition. Also, the net torque acting on the system has to be zero. Right? If there's a torque acting on the system, obviously that system is not in equilibrium. In this case, net force acting on the system is zero because we got two forces acting on it. They're in opposite directions and they have the same magnitude. Except there's going to be a torque on the system because these forces are acting on it relative to a point of rotation, axis of rotation. So this is going to cause a rotational motion. So you cannot have that, which means that the net torque has to be zero as well for equilibrium. So which means that we got two conditions for equilibrium. The first condition is the net force acting on the system has to be zero. So what that means is the net force along the x direction has to be 0, along the y direction has to be 0, and along the z direction has to be 0. That's what it means. The second condition is the net torque of the system has to be 0.